Previously, we let theta of t equal pi over 4 radians per second times t. So that when we multiply by a t in seconds, we're going to get an angle in radians. And that's going to tell us where the particle moving around the circle is at that given time t. The function we got in this case, assuming the circle of radius 10, was 10 centimeters cosine theta I plus 10 centimeters sine theta j. We could have factored out the 10 centimeters and ended up with just cosine theta I plus sine theta j. If we let r of theta of t equal the function we saw previously, then we get motion around the circle in time. Now we're going to let omega stand for the rate of rotation around the circle, or the rate of travel around the circle, instead of the pi over 4 radians per second. And we're going to have theta of t equals omega t, giving us the function r equals a cosine of omega t I plus sine of omega t j. A would be like the 10 centimeters we had previously. Omega would be like the pi over 4 radians per second. Now this describes a vector from the origin to a point moving on a circle of radius a. We can calculate the derivative of this function very easily. The derivative of cosine of omega t is negative omega sine omega t. Multiplying that by the a, we get this. And the derivative of sine omega t is omega cosine omega t. Multiplying that by the a using this distributive law, we get this expression for the derivative of the function with respect to clock time.